So we have again a metric space. Xn is a Cauchy sequence. And then we think about the set Xn, right? So this is this subset of X, and I claim that this subset here, so A here, is bounded. Okay. Now, why is that the case? So since Xn is a Cauchy sequence, if I choose epsilon with epsilon, say equal to 1, you have that there exists capital N, so that if little n and such that if little n and little m bigger than capital N, then the distance between the two is smaller than 1. Right? This is just using that it's a Cauchy sequence and just using one particular epsilon, namely taking epsilon to be equal to 1. So now, of course, this means, and now you don't need this even for all of this. You don't need it like this. You just need, so in particular, therefore, as long as n is bigger than capital N, well, you can use you can use m here. You can use capital N for m. So then this here say, therefore, for little n bigger than this, we have that this thing here, the distance to this is smaller than 1, right? And so now, you have that if you now such a set R equal to 1 plus the maximum of the distance from x capital N to xi, where I here runs from 1 up to capital N minus 1. So there are n minus 1 of these, right, that you take the maximum over. Right? So if you define little r to be like this, then obviously little r is some positive number. It's finite, right? And you have that, and now I claim that our set A here is contained in this ball here around Xn. So I claim this thing here. Okay. Now let's see, so why is this the case? So if X here, if capital, so we need to prove that we need to show that for all n, you have that the distance here is less than r, right? If that's the case, then the whole set here would lie in this ball, right? But you see that if n here, well, if n is bigger or equal to capital N, but this, remember that then we have So this is, right, so we need to show this in here. If little n is bigger than capital N, then we have that the distance from this little n to this one here, right, the tail was less than 1, right? But this thing here is actually, right, this is actually less or equal to r, because it was 1 plus this maximum, and then this is maximum over non-negative numbers, right? So you see that for the whole tail, we have this property. But for all the other ones, right, for n less or equal, less than n minus 1, right, these are the remaining ones. Well, there, the distance from xn to x, capital N, well, this is one of these guys, right? So it's clearly, this one here is clearly less than capital R, right? And it's really strictly less than, because there's this 1 also, right? Yeah.
Does it have to be 1 plus the max, or could it be the max of 1 for all of those elements in the sequence?
I wanted this one here to be strict. It's just a silly thing, but that's why I took it like that. Yeah, because otherwise this would be strict. But it's just a trivial thing, and it doesn't matter very much. At this stage, it makes no difference actually. But it was just to use this. We'll talk a little bit more about the ball, because there is another way. You know, you could define the ball. Maybe I'll say a few words about that now. Okay, so this here, so what this proves again is that in any metric space, a Cauchy sequence is automatically bounded. Fine. And so remember, in any metric space, a convergence sequence is a Cauchy sequence. So a convergence sequence is also bounded. Fine. And now there's this question, which is a natural question, and this is connected to the definition of ball. So the way we define, and it's actually worthwhile emphasizing, because it's useful in the next thing that we want to get to. And so when I define a ball, I assumed, so the definition of the ball, let me just write it up again here. So the definition of a ball in a metric space, these are the y in this set, so that the distance to the center is strictly less than r. Right? You could, of course, have defined it differently. You could define it that this is strictly, or instead of strictly less, less or equal to. Right? I want to use strictly less here. Yeah. But sometimes, if I want to be very clear, I will talk about open and closed ball. And this is what we're getting to next. Right? And so when I'm talking about open ball, but I'll try not to use that term here. But open would always mean this. Closed ball would mean that it's less or equal to. Sorry. Yeah.
When you were talking about like the neighborhood example,
yeah.
Like, does that refer to like is X in that case like a subset?
Yeah, that's right. Exactly. That's right. And so now, and I didn't, you know, this I didn't actually I already posted the lecture notes, and so in the lecture notes I didn't actually talk about tubular neighborhood, but it maybe is worth thinking about. So you could look at us at, so you have a metric space here, and you could have a subset. A is a subset, any subset of the metric space. And you could define the tubular neighborhood of a subset, and so you could do this similarly. So this would be the y in X, so that the distance from y to x here is strictly less than r for some x in A. You see what I mean? So this here is like, this is how, so again, if you think about our tree, you take some, I mean, maybe we shouldn't talk about, maybe we should draw it more crazy, like some curve maybe. And if you're looking at the set that have distance at most, this is like some sort of tube like this. Right, this is like, this here would be the sinks. And then here at the end, it would look like a cap like this. Right, this here would be like a tubular neighborhood of this curve. Right? Yeah. Okay. And so, as you were saying, that in the case where A here is just a point, then those two coincide. Okay, so now, like one of the key things when you're thinking about convergence in R, remember that this stuff, and we use this time and time again, that it was often, we saw this for series, that it was often difficult to determine the exact limit of a series, right? But the question was always, does it converge, right? And so if it converges, then often, also if you were using this in some sort of application, it's often in all kind of fields that it comes up that things are written in terms of a series, and it's not clear what it's converting to, but you want to know whether it's converting. And then you also want to estimate what is the limit within a certain error term, right? And you can use some of these comparison tests to determine, to estimate how close you are to the actual limit, okay? But in any case, right, the thing is, it's very useful to have a criteria that is easy to work with, and that say that it's converging without having to be able to find the limits, right? And like the Cauchy sequence, this was like a notion of that, right? And so the key on R, the key for using that was the Bolzano-Weierstrass theorem. So this was the one that was the key for using to get the Cauchy convergence theorem. So the Bolzano-Weierstrass theorem so remember that this is 4R, and it say that any bounded sequence has a convergence subsequence. Right? That was Bolzano-Weierstrass theorem. In a general metric space, this, it makes sense to talk about a bounded sequence, right? But it's not always the case that a bounded sequence has a convergent subsequence. So it does not hold. The Bolzano does not hold. So warning, Bolzano-Weierstrass does not hold. In a general metric space. And in fact, of course, the example that we looked at where the example was X here, like this, and where we're looking at that sequence, this is a bounded sequence, but it's bounded, but it doesn't have a convergent subsequence. Right? It's actually a Cauchy sequence, but it doesn't have. Right? So it doesn't hold in a general metric space, but it does hold. It does hold if the metric space is compact. And so that's what I want to talk about next. But in order to talk about what it means for metric space to be compact, then I need to talk about, I need to define what it means for a set to be open. Okay, so we need the notion of an open set, an open subset of a metric space. Okay, so we have a metric space again, and so A here is said to be, let's call it O for open. O is said to be an open subset if for all x in O. So the idea is that you have here, this here is O. So O is, this is maybe O. And so the idea is that for each element, there exists some ball centered at that point. So for each x, for all x in O, there exists r greater than 0. It may be incredibly small, so that not just x, but the whole ball around x is contained in the open set. So you see that not just this point here, but the whole ball here would have to be contained in O. Right? So in this picture here, when I'm illustrating this, I'm thinking about x's being R2, and I'm thinking about the distance being the usual Euclidean distance. Right? And then, but then actually, if this is open, it means that you cannot include these points here on this curve. Right? They would not be included in the set, because if you take any point on this boundary here, so to speak, then a ball, part of it would be outside the set, right? So if this here really was open, then this curve here was not included. And you see that as you're getting closer and closer to that curve, you know, you can still have a little ball that is inside the set, but as you're getting closer, the radius of this little ball have to be smaller. Right? But that's fine. Okay, so this is what it means for a subset to be open. And the first thing that you observe that with this definition, there are always two open subsets. So again, this thing here. So note that the empty set, but there's no condition. If there was an empty set, it's say for all element in the set, but there is no element, so there's nothing to be satisfied. So the empty set and all of x are open subset. Okay, so do note that, fine. So in particular, if you take, if x here was not the whole real line, but it was just an interval from 0 to 1, and then the distance between elements was the usual distance, then actually even the closed interval, which is the whole set, would be open, right? So you just should be careful with, you know, what the set is, right? What the set X is. Okay. So now, right? So now the key here is that so if you have an open set, you know, how do you kind of construct well, maybe the first thing I should do is I should prove a lemma that is the following. And then after that, we will talk about how to get lots of open sets. So we have two examples. At the moment, we have two examples of, so if you take a metric space, at the moment, we know that there's always two subsets that are open, the empty set and X, but they're not very interesting. So a more interesting example is that if you take a metric space and you take a ball, and now it's crucial how we define the ball. And so it's crucial that this inequality is strict, okay? So for a metric space, X here is in X, it could be any element in X. This thing here, R here, is positive, strictly positive. It also has to be strictly positive. Then this thing here is open. Any metric ball like this is an open subset. Okay, let's try to prove that. And again, when you're proving things like this for a metric space, the only non-trivial thing is the triangle inequality. So this is relying on the triangle inequality. And so for a lot of things, when you're proving things about a metric space, it's often quite helpful to draw a little picture. So, but of course you have to be careful with, again, that then the intuition comes from, you know, Rn, and sometimes the metric is a little bit more complicated than that. So this here, imagine that this is the ball of radius R. Here you have some X. Now take an element Y. So suppose that Y here is now in this ball here. Then we want to show that there exists that for some S bigger than 0, the ball here of radius S around Y is now contained in this ball here. So here you have Y, and we want to prove that there's some little ball around Y that is contained in the original ball, right? And so again, this is going to rely on the triangle inequality. So you have Y here. Y was supposed to be in this ball here. This means that the distance from X to Y is strictly less than R, right? You take now S here to be R minus this distance here. Okay, why do I do this? Again, in my picture here, I have here X, I have here Y, and our intuition is that if we kind of go from X and we go through Y and then we go straight to the boundary, then this thing here is dx comma y, and this one here is R minus dx, right? This is the remaining. This whole here is R. This here is dx comma y, so this here must be this here, right? And so if you're setting this equal to S, and now you imagine taking a ball here, well then, at least on the picture, this whole ball is contained in the original ball, right? So let's try to see if that works, right? If that works, then it really only uses the triangle inequality. So we're setting S equal to this, and then we're looking at this ball here around S. And we take an element here in this ball, and we now need to prove, so we need to show we want to prove that this whole ball is contained in the original ball. So this means that we need to prove that for any such element, Z here is in this thing here. Right? That's what we need to prove. And so now you see, so we take so we take C. So we're now looking at. So we're going to look at this distance. Right? In order to prove this, we need to prove that the distance from C to X is strictly less than R. So let's examine that distance. Triangle inequalities say that this is bounded by the distance from X to Y plus the distance from Y to C. This one here, from Y to C, C lie in the ball of radius S around Y. So this means that this thing here is strictly less than S. Right? And so you see that this thing here is now less than dxy plus S. Now you fill in what S is. This here, S was equal to R minus dxy. That was the definition of S. And so now you see that this thing here is R, right? Because those two things cancel out. And you see that this here guarantees you that the inequality was strict. Right? And so, right, so it really is that whole ball was, so we conclude that this whole ball here was contained in the original ball, right? And again, the proof of it was just from this picture, right? That you make kind of rigorous, and the only non-trivial things at the moment we really have in a metric space is a triangle inequality, right? Because we haven't built up a lot of stuff. Okay, so this, you see, this immediately give you a lot of example of open subsets of a general metric space. And if we had looked at exactly the same stuff, this with tubular neighborhood, we would find that those are also open subsets. Yeah.
Are we also going to look at closed subsets, or do those like have a value?
Close, yeah, very much so. But we haven't defined what it means to be close. But you're right that, and we'll do this. You're right that, so at the moment we don't know what a closed thing is. You know, and maybe I will just define it, and then then we can. So okay. So let's define. So I'll talk more about this next time. But now when you're asking. So again, so we have X here is a metric space again. And then C here, it's a subset of X, is said to be closed. And then now it may seem almost cheating. It's said to be closed if the complement so this means that the complement of C, so the complement of C, so the complement of C, the complement of C, right? These are the X, all the X in X, so that X is not in C. Okay? So the complement of a set is everything in X that is not in that set. Okay? And a set is said to be closed if the complement is open. Okay? And so now, once you have this definition, and I'll prove this next time, that if you're looking at what I denote like this, so this is the elements where the distance to x is less or equal to, so this here is not any more strict, right? This thing here is then a closed set. Okay.
Could you also define it by like the way we define an open subset, but saying that R instead of being strictly?
No, I couldn't define it like that. Yeah. Right. But so, I mean, you could define it other ways. There's another standard where we'll talk about, there's another equivalent to say that if you take, but I don't want to get into that because, you know, but there's another way. We'll get to this in just, and closed sets we really mostly talk about next time. Right? It was just because you were asking. But let me just talk about, so this here is one, but I'll just repeat this in just a second. So in order to produce more sets, so we start with, actually I should just note, although, you know, just now when I talk about, you know, just the definition, I should just immediately note that there are always two closed sets. Because, you see, the empty set was always open and the full set was always open, right? And so the complement of the empty set, that's everything. So that's closed. And the complement of everything is nothing, it's empty set, right? So that's also closed. So those two sets are always closed. But let me just talk about, so I want to think about, you know, how do you produce open sets? So how do you know that there are a lot of open sets? And so if you take sets, so this is like operations on sets, on subsets of a given set. So here I'm thinking about just X as being a set. It does not need to be a metric space. So if I take a set, and I take two elements, two subsets. So these are two subsets. Then I can form the union of these two. This here is the union. And the union here of two sets. So the union, and again I denote it like this, cup, like this. These are the elements in X such that X is in U1 or X is in U2 or both. Right? And so you often illustrate this with, like, if you have this here is X, this here is U1, this here is U2, U1, and U2. Then this thing here is the union. And likewise, the intersection is things that is lying in both sets. Right? So the intersection so this is again, you have these two sets, and this here is the intersection. So, and you denote it like this, and this is the X, so that X is in U1 and X is in U2. That's the intersection of these two sets. Okay, and then there's a third, and then we talk immediately about generalization of these. So there's a third, and this is this with a complement. But let me also introduce the notation. So if you take this subset of X, then the complement, and people, there are sort of slightly different ways of doing it, of defining it, or not defining it, but of notation for it. And I always use this one because I think that's the clearest one. So this is like X take away U, and this is totally standard. There's another one that's often used where you have C that's slightly less standard than this one. And sometimes it can be confusing. This one can never be confusing. And so this thing here is a complement, and so this means that it's the X such that X does not belong to U. Okay. And so now, okay, so that's like standard operation of sets. But there is a generalization of this union here, where instead of just two sets, you could take potentially infinite many sets. So if you take a family of subsets, so if U alpha here is a family of subsets, then you could look at the union of the U alpha. This is like denoted like this, and this is the X in X, such that X is in U alpha for some alpha. I mean, it could be in many of the U alphas, but it has to be at least one. Right? So this is the union of a family, and likewise the intersection of a family is the X, and then it has to now lie in all of them. Right? It's X in X, where X is in U alpha for all alpha. Okay, that's the union and the intersections of family. Okay, and so now let me look at some example. In particular, let me look at an example of this. And then let me prove something about open sets. So let me look at an example here. Suppose that U alpha or UN, I'm just going to look at, it's going to be now a family of subsets of the real line, and they're going to be indexed by the natural number. So this thing here is going to be minus 1 over n to 1 over n. And if I'm looking at the union of these guys, but you see, this is a sequence of open sets, right? I mean, it's like for each n you have an open set, but they are, as n get larger, they're smaller. The first one is the biggest one. So if you take the union of these guys, that just gives you the first one you started with. So this is the union of these, right? If you take the intersection of them, well, the only thing that is in all of these sets, that's actually the 0. Right. Okay. Now, now we need some stuff about operations of sets. And so how does things, and so there's some standard operations, and my recommendation is that not try to remember this. I don't remember it myself, so I always have to kind of run through, but once you have done it once or twice, the proof is so trivial that it's not worth remembering, and I think if the danger, if you try to remember these things, you may remember it wrong, and that's much worse than just running through the proof. So, you have the following lemma here. So you have a set, and then you have subsets. Let's call it A, B, and then a family of subsets. And the thing is, the first one is that if you take the complement of the complement, so if you take A and you take everything that is not in A, right? So just think about it that if you take, so here you have X, here you have A, this is A. If everything that is not in A, that's over here, right? But then if it's not over here, then it's A. So the first one is just that, right? And actually we sort of, just because we're also running out of time, right? We really proved this, right? I mean, so if you have something that is not in A, then it's lie here. But if it's not lie here, then it lie there. That's that statement. Okay. The second one is that if you take the complement of that, it's in the union of these guys. So if it's not, this just means that it's not in any of these guys, right? This here is the set. Imagine that you have something that looks like you have a bunch of sets like this. These are this is supposed to illustrate the A alphas. And if it's not, this here say that if it's not in any of these, well, then the claim is that then it's in the intersection of that it's not in this one, it's not in this one, and it's not in this one, and it's not in that one, right? So that's also clear enough, right? So this is the second one. Again, I actually wrote out the proof in the notes, so you can check that out. And the third operation, is that if you take X and you are removing the intersection of this family. So this means that it is not. So this means that the intersection of the family, in this picture here, would be this thing here. And so it's not right there. Everything else is allowed, right? But that's the same, you see, that's the same as the union of X take away, right? This here is the element that is not in one of, there's at least one of the U alpha, A alpha, where it's not in. Right, and so that's the same. So this is the same as this. Okay. Again, I wrote it out in the notes, the proof actually, right, of these things, right? Okay. And let me just say, maybe we can't quite. We'll pick up in the notes where the other stuff. But let me just say that when you prove this sort of thing, and we even did this here when when I'm just illustrating it with a picture. So we prove it using the following sort of trivial lemma, and I wrote that out as a lemma in the notes, that if you are trying to prove that two sets are equal, right? So suppose you're trying to prove that two sets are equal, then in a way it's natural to divide this into two parts. So this is the same. As proving that A is contained in B and B is contained in A, right? So if you're trying to prove that two sets are equal, then you would prove that for any element in A, it's also in B. This is this thing. And you would prove that for any element in B, it's also in A, right? And so that's when I wrote out the proof of these three things, then I wrote it out like each of them has two parts, right? that you prove that this set is contained in that, and you prove that this is contained in that. Okay. Now, right, we're almost actually there. So now, let me just say that. So that's actually in one of the p-set problems, but there's no p-set. You have a little break now for p-sets because I want to make sure that there is no p-set in material we haven't yet covered in class. So that's why there's a break. And anyway, all of the p-set at this point are actually posted. So the last one I think is due, I forget whether it's the 8th of May or something like that. And there's 5 left. You've already done 5. Okay, so now if X here, B is a metric space, then you have the following lemma, that if O alpha are open subsets, then the union of the O alpha is also open. Right, and this is actually, but this is quite trivial as you see. I'll just indicate why, but it's actually left on a p-set. So to prove here, but I will just illustrate it anyway, that if you take an element here in the union, well, this means that there exists it means that X is in O alpha for some alpha, right? For some alpha. But this means that there is a ball around it, because this here is open. It means that there's a little ball around it that is contained in this, right? But therefore it's also contained in the union of these guys, right? And so this is really just a proof that the union of open sets are open. And next time, we're out of time now, but next time we'll talk about why, if you take finitely many sets, why the intersection of finitely many sets, of finitely many open sets, why that is also open. But for intersection of open sets, you have to be careful, because for union, you can take the union of any number of open sets, it's always open. But if you take intersection, in general, it's only true that finite intersections are open. And the example is one of the examples we looked at before, where you take these sets here. These sets are open subsets, but if you take the intersection of all of them, then you just get 0, and that's not an open subset. Okay, so we're done.